there, friends, and welcome to another episode of Fun Times and Statistics. I will be your host, and today we're going to be talking about multiple linear regression. So, we're going to do some things today you've definitely seen before because we did them in simple linear regression, but there's going to be slight changes in the fact that we will do multiple of them, hence the name. This should be pretty fun. So the data we're going to be looking at today does seem to be a smaller data set, but everything we do we can apply to larger data sets just to keep yourself on track with where you should be. So in particular, we're going to be looking at some thermal energy data from solar panels. So the idea behind this is that when you have a solar panel, if it gets too hot or too cold, too fast, woo, it can end up cracking and or warping the glass, and I don't know if it's glass on top of it now that I think about it. I don't know that much about this. Oops. It might be glass. All I know is it can damage them and make them unusable. Unusable. Ooh, words. So what we want to do is we want to be able to predict what's called heat flux, which is how much the heat or temperature change. Sorry, temperature is a measurable item. Heat is a unit of energy, so I have to be careful with that. We want to keep track of heat flux, how much change it's experiencing, and whether or not that I can predict that, and if I can predict it, then hopefully I can position my solar panels so they get less heat flux and therefore are less likely to be damaged. So we have a couple different variables happening in here. I have some descriptions of them. These are all directional. You should notice that there is no west variable because, well, the sun rises in the east and sets in the west. And if you're keeping track of east, you don't need to keep track of west. But north and south, not so much. There's also time of day. You should expect this to look like, well, what you should expect from the sun rising and then setting. And then insolation is exactly what it is, insolation. So we're going to be trying to predict heat flux here. Let's get into practicing this. So the first thing we're going to look at is we're going to check some of our stuff before we wreck some of our stuff. That was vague. I want to check to see if it meets the conditions for even bothering to try to do a linear model with this. So I'm going to start with doing a scatter plot. Do not make the mistake of starting with correlation. Remember, one of the requirements to be able to use correlation is you need to have a linear relationship to begin with. You really should always do, I shouldn't even say really, you always should do scatter plots first to check for linearity. Correlation does not tell you linearity, it just tries to measure how strong of a linear relationship there is. You have to do scatter plots to do that. That's like rookie mistake number one. Go right to correlation. Alrighty, let's go ahead and produce ourselves some scatter plots. So I'm going to do this a little differently from what you saw last week. So I'm going to graph, scatter plot, simple, and here's where things are going to change. So last week we were doing some of these and we just had 2 variables, but now I have 5 possible predictors I want to look at. So I'm going to throw heat flux in for y, and then I'm going to have 5 of these, one for each of my variables. Heat flux in east, heat flux in south, heat flux in north, heat flux, and time of day. I am going to be sick of saying heat flux by the time this is over. Come on. There we go. I'm going to do one slight difference that you don't have to do since I have a small screen here. I'm going to do multi-graph and put them all on one image. So I'm inlaying them in panels on the same graph. You do not have to do this. If you do not do this step, it'll just accordion 5 of them across your screen. I want to put them all together so I can compare them and talk about them all at once. Here we go now. All right, so north is the nicest looking one here. So it looks pretty straight, which is good. What I'm looking for is linearity. I would say north is going to be good. Insolation has got some scatter, but it looks pretty straight as well. It does have a cluster of points over here, which just means that I have more data that looks like this. Don't let that fool you. We're looking for vaguely straight shapes, not curves. This is really hard to call. With east, kind of looks like that, but lots of scatter. South, maybe like this, but lots of scatter still. Or it might be a loop. That one's kind of hard to tell. So, And then you get down to time of day and you're like, ding! That's not linear for sure. That's very curvy. So this is the reason why we have to do scatter plots, because correlation is definitely not going to show us this. So I definitely want to keep north, definitely want to keep insolation. Definitely do not want to use time of day. No time of day because it is clearly nonlinear. Since east and south, I'm questioning whether or not I should include them. I'm going to include them, and likely what will happen is if they turn out to be not good linear predictors of heat flux, they'll get removed by the stuff we do later anyway. So, when in doubt, include them. So if you're not sure and they're not as clear as a bell as the day, or that's not a phrase, if they're not as clear as time as day is for the curvature, you are going to include them. So we're going to include east and south. I'm going to go ahead and minimize this so I can save it for later. I don't think I'm going to need it, but that's all right. Now that I've eliminated a variable, I can go ahead and move on to correlation. So we don't really need to do correlation to do this. I just want to practice it. So I'm going to go to stat, basic statistics, down to correlation, throw in everybody in there. I'm not going to include time of day because I already know I'm not going to use it. And then I'm going to go ahead and uncheck the box for display p-values. You notice that since I did a range of stuff, Minitab is just making notes. I do this through with a little dash to north. That doesn't mean I didn't include everybody between them. I'm just going from here, dash to there. Let's hit OK. And let's see. All right, so like we already suspected, since east and south were kind of weak, and you notice that they do have weak correlation, insulation's pretty good, and then north appears to be the strongest. So that's interesting. So east and south look like they're not going to be all that positive predictors, but remember, when you're looking at your predictors, they're working together to make their predictions. So it could end up that one of them, like maybe east, will account for some of the things that we might be missing if we didn't include it. So I'm saying that if you started with maybe like only the north variable, oh, you know, maybe south is going to be able to like not do much, and so therefore it won't make your correlation, sorry, or your relationship be more of the variation explained. In which case, you know, I probably need a different variable to include. Maybe if I throw in east, since east and north face different directions, east accounts for the rest of that. That'll improve my r-squared value and therefore give me a better model. So let's take a look at this. So what am I doing next? Oh, let's make a model now that we decided who we're going to use. Woohoo! So I'm going to include everybody in here, even though these two are weak, just to see what happens. And I think you might be kind of surprised. So we're going to go up to stat, regression, fit regression model. Please notice I'm using something different from fitted line plot because fitted line plot will only use one variable and only will do simple linear regression, and we're interested in doing multiple today. Let's go ahead and click on that. So for response, I'm going to throw in heat flux since that's the thing I'm trying to predict. And then in the continuous predictors box, I'm going to double click in all of my other variables, but again, no time of day because it is not going to be included. So as you look at these are continuous quantitative predictors. Continuous is a type of quantitative data. Notice that they are not categorical predictors. So you can do these models with what are called binary or categorical predictors. So if you want to include a categorical, you can, but you have to put them down here in this box. Do not put them in the continuous box. That will definitely produce the incorrect model when you're looking at this, just so you know. I'm not going to mess with any of the rest of these settings yet. I know if you look down at number 5, you're anticipating, oh, I got to check equal spread nearly normal. That means I'm going to need some residuals. I don't know that if this is going to be a good model yet, so there's no point in going ahead and hitting the graphs button at this point. So let's go ahead and hit OK and see if it is a good model. Woohoo! Be careful, that little twirly box is okay. Sometimes this will take a little bit longer because it does take a lot of computing power to do this. Let's take a looky-see at what we got. So first step, S is fairly small. When I ask myself if S is small or not, I always want to be comparing the value I see here, 8.1 and some stuff, to the values relative to what our response variable is. So I want to compare it to heat flux. These are all in the 200s. So think of this in terms of money. If you needed to be paid around $250 to $300 and someone, you know, shortchanged you $8, that's not such a big deal. But if they shortchanged you like $80, that would be a bigger of a deal. So what I'm saying is that relatively speaking, 8 is small compared to 2 to 300. So I think that this is okay. Next up, I want to look at r-squared adjusted. Be careful, since this is a multiple linear model, I don't want to look at r-squared, I want to look at r-squared adjusted. 87% isn't too bad, so I'm able to account for about 87% of the changes I see in heat flux using these 4 variables. Let's see how good of a job those 4 did. So what I'm checking next is what's equivalent to the slope test in the previous chapter. So what we did in chapter 15, we want to ask ourselves, are these significant predictors of heat flux when they're working together? Remember, this is not individual. So you go over here and you look and you're like, ooh, north and south, both are significant contributors. I wasn't expecting that because since they're kind of opposite directions from each other, I was kind of expecting south with how bad of a correlation it had to not be significant, but it looks like we should be keeping it. And then east is a little weaker, but it looks like it's still significant. But then insulation is coming in with a p-value bigger than 5%. And when you have a big P, That means you're going to reject that hoe. So it looks like insulation is not a significant predictor of heat flux. So what I want to do is I want to remove the insignificant one. So I'm going to remove insulation because it is not significant. So I'm going to have to run my model again. I'm basically at step 4 now where I'm like, oh, I had some insignificance. Let's remove them and then repeat. Rinse and repeat. Only remove one variable at a time because you might be surprised on what it does. And therefore, if you remove more than one, you're seeing too much. It's like skipping ahead to the end of a book. You miss all the meaty stuff. You might miss something important is my point. Let's click Edit Last Dialog. All right, I'm going to throw out insulation, so I'm just going to highlight and delete that one. And then I'm going to run it again with east, south, and north. Alrighty here, let's go down and see what happened. So you'll notice my R-squared adjusted did drop some. That can happen. My S got just a little bit bigger. This does not mean that this is a bad model though, because you want it to have everything being a significant contributor. Ooh, look what happened to east. Now east doesn't matter. Turns out all you need is north and south, which I found kind of fascinating. When it came to heat tracking, you need to know the north and south position, which kind of makes sense when you think about it, since the sun is always going to be doing the same thing. So it looks like east is insignificant, so I'm going to have to remove that guy. So we're going to go to Edit Last Dialog, go ahead and throw out east, and then hit OK. Alrighty, our R-squared adjusted did drop again, our S did increase again, but these are not significant changes in my mind. And now I have everybody being significant. This is what I want to see. So again, I want to see p-values that are under 5% for everything. So then the next thing I look at is my regression equation. This will be the final version of it, which is kind of interesting. It looks to me like the intercept is insignificant because it's showing up way bigger than what we could possibly get as a response. Alrighty, so now that I have my model that I'm choosing, what I need to do next is analyze, did it work right? I mean, is it a good model? So I want to check equal spread and nearly normal. I mean, the R-squared adjusted alone is enough to tell us it's pretty good, but, or I was able to account for almost 85% of what was happening. Sorry, I have to pause and cough. Sorry about that. So now I need those extra graphs. I'm going to have to run this again, unfortunately. So we're going to hit Edit Last Dialog again. We're going to hit the Graphs button. And I want my residuals. Oh, sorry if you heard that real loud. I want equal spread and nearly normal. So I'm going to go ahead and choose residual versus fits. And then I know you guys like the histograms of residuals, but I'm going to use the normal probability plot because I think it's easier to read. And then the last thing I'm going to do is something I haven't done before. You do not have to do this. It's entirely optional. Your results come out the same even if you do this. Is I'm going to change this from regular to standardized. So what I'm doing there is I'm going to have it using z-scores instead of the standard data. So that's going to allow me to look at not only position and shape, but I'll be able to see, like, well, not only shape from the graph, but I'll be able to look at position as well, like how far is everything from the mean. So are my more extreme values the ones that are doing strange things? Let's go ahead and hit OK, and hit OK again. Again, that's entirely optional. You'll still get the same results when you're analyzing these. So let's take a look at the versus fit first. Make this a little bigger. There we go. We are looking pretty good here. So when I'm checking equal spread, I want to see is there about the same number of points or dots above as there is below. That's looking pretty good. Hopefully you're seeing where the standardization is coming out. So it looks like I do have some, values that are hanging out by themselves, but they are, they're kind of far from the mean. They're a little unusual. And you might be tempted to say, oh, it looks like equal spread is fine. This does have a little bit of a cone shape, but not a super strong one. However, if you play connect the dots the right way, you will notice that this does have a pattern to it, which means it violates the equal spread condition. So let me show you what pattern that has. Ready? If you go like this, you'll notice it has a sort of nice zigzaggy wave. Yeah? Do you see it now? That one's not an easy one to spot, but if you've been doing this long enough, they get a little easier to see. So this means I definitely systematically missed something with this model. And the answer is you really should include time of day, but as a quadratic factor, not a linear one. So if you want to do a regression model that has linear and quadratic factors, you can do a better model than what we have today. And it's much stronger than what you see here. The problem is that in Stats 2, we don't do the quadratic stuff. So if you'd like to know more, I will gladly teach it to you. Send me an email. It's just that we're out of time. And so we're sticking to what we can do. So this looks pretty good, except for it has a pattern. So we should be cautious about using these results because we clearly missed something. Let's minimize that guy and check out nearly normal. So you can see the pattern even in the nearly normal, which is a little suspicious, right? Do you see the waving? Whee! Anyway, since most of our points are close to the red straight line, that means everything is pretty close to normal. There are a few points where above the 5% mark where I'm pretty far from normal. There is a pattern here. It's called an S wave that you really don't want to see because that does mean you miss something. But as far as nearly normal is concerned, it seems to meet the nearly normal condition because most of the data is close to being normal. Remember, the red line represents normal. Alrighty. I would say we meet the conditions slightly, but we should question using our results since clearly our residual is showing a pattern that we missed with this data. Good times. Now, I used to call this when I was a student the hokey pokey method because you put the variable in, you take the variable out, you shake it all about, and that's what comes out. It is what it is. As it turns out, Minitab will automatically do this for you. So what I want to show you now are some methods to do that. So I'm going to look at two different things. We're going to look at what's called stepwise regression and then the best subsets regression. So what stepwise is going to do is exactly like what we were doing today in the let's remove a variable every time it's insignificant. We were doing what's called backward elimination, where you start with all of your variables and eliminate until you get down to the stuff that's significant. The way I like a little bit better is what's called the best subsets regression. It's where you will take all of your variables and Minitab will do every single model it possibly can in all combinations of those variables and report out to you the best ones for each size. So using 1 variable, 2 variable, 3 variable, 4 variable, or 5 variables in our case. And then we get to pick from that list who we want to use, which is kind of fun. Now, when you're doing best subsets and stepwise, they might not come out the same. Since we only have 5 variables, my sinking suspicion is that they will come out the same in this case. And remember what you're trying to do. You're trying to predict as much as you can using as little as you can so that you're not over predicting your variable. What do I mean by that? Well, you got to look at what's called Mallow's Cup. If you know what a Mallow's Cup is, it's a lovely dark chocolate marshmallow treat that is very popular in Britain, which is probably how this got its name, but I'm not entirely certain that's true. What do we need to know about Mallow's Cup? Well, it's a measure, kind of like correlation, that tries to tell you if you are overfitting your model or not. So what we want to see is we want to see a Mallow's Cup that is small and close to the number of predictors plus a constant. So if I was doing a model with 5 predictors, I want to see a Mallow Cup close to 6 because I had to have 1 more for the constant. So we're going to use that as our way of did I overfit. Here we go. So the first one I'm going to create is the one for number 6, which is the stepwise. So to do this, it's actually pretty simple. We're going to go back to stat regression, fit regression model. You should notice down here that there's this stepwise button. Ooh, we didn't use it before. Now we're going to go ahead and click on that. Alrighty, right now it's not using the stepwise method. That's why it says it's none. We want to use backwards. Woohoo! I have screwed up already. I need to have all of my variables in there. Sorry. I have to give it the choices. So what I'm going to do is throw in all the variables and let Minitab decide. Dun dun dun! So we're going to hit the stepwise button. The music is annoying. I really shouldn't do that. Right now it's not doing the stepwise method, so it's selected none. We're going to change that to backwards elimination. So it's going to have all of them to choose from and it's going to eliminate. So what I'm going to be careful about here is this value, alpha to remove, your level of significance. Remember, our alpha we like to use is 5%. If you want to have a little more wiggle room in your model, you can choose a different alpha. So I'm just going to use the standard 5%. The last thing I'm going to change is I'm going to change from details about this method to include each step. So it shows me what it's doing every time it eliminates something. Once you've got yours set up like mine, you can hit OK. OK again, and this might take a minute because this is a little more complicated. Here we go. Oh, it's producing the same graphs. Oh, that means it came up with the same model I did. That's not a shocker. Let me teach you how to read this real quick. Come on. There we go. So it's going to take you through each step. So it's got the constant value and then the variables themselves. Then it's going to release the SR squared. And down here we have the Mallows cup. So starting out, if you're using all 5, the Mallows is looking pretty good because it's floating around 6. However, this is probably an overfit just because it's using everything, and you'll notice that, ooh, some of these p-values are not significant. Namely, look at time of day. It's huge. So of course, Minitab selects that one to remove. How do I know that time of day is the one that's removed? Because notice in the next column, it's gone. So you take a look at step 2, and then you look at step 3, and you ask yourself, well, who did it remove at step 3? Blank spot here, it removed insolation, the one we removed after removing time of day for not being linear. And then it did the same thing we did. It's like, hey, east, no, bam, done. That's the final one. Now, the only thing I'm concerned about this is notice what happened to our Mallows. It went down, which was a good thing, but then it went back up. Usually that's a sign that you maybe made the wrong move here. It is interesting that it came up with the same method, the same model we did using the same method. So you can automate this, as you maybe suspected. Let's take a look at best subsets. I actually like best subsets the best because it gives you all possible models. So here we go again. I'm now on 7. We're going to go to stat, regression, and now slightly different. I'm going to select best subsets. So it asks you for your response. We're going to throw in heat flux. Now you have the option between what are called free predictors and predictors in all models. So if there's a variable you are 100% certain you want to use, you're going to throw it in predictors in all models because it's going to force Minitab to always use that one. Since I kind of am loosey-goosey about everything and want it to show me all the possibilities, I'm going to throw everything in free predictors. There we go. As always, let's check our options. Woohoo! Now, I'm going to change some things up in here. So the minimum of free predictors is always set to being 1. That means you must have at least one variable to run the method, which makes sense. You wouldn't try this with none. You can also set it at a maximum. So if you have something that has like 20 possible predictors and you're like, there's no way I'm using more than 10, you can set the maximum. I like to change this from models to print from 2 to 3. If you leave it at 2, it just gives you the top 2 of each size. I like to see the top 3. This is just a personal preference. It is not required. Let's go ahead and hit OK. And OK again. And this one usually takes long. Wow, that was blisteringly fast. That makes me a little scared. Usually that one's the one that like can kill your computer on accident. So if you have an old computer, maybe don't do this one. So this one's kind of hard to read. Gonna teach you how to read it. So we've got some stuff here. Pay attention to the stuff at the top of the column. So there's our R squared, don't care. R squared adjusted, then I do care. There's our Mallows, there's our S value. Notice they're kind of all over the place. I'll get into that. Here's our insolation variable, east, south, north, and time of day. So basically the little X's mean that in each of these models, if it has an X, that was the variable that was used. So for instance, this middle number 2 used north and time of day. So you hopefully look over here and notice that this doesn't go 1, 2, 3, 4, 5. It goes 1, 1, 2, 2, 2. Sorry, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, and then 1, 5. What's happening here? Well, this is the number of variables. So this is the top number. These are the top 3 ones that use only one variable. So there's 5 options for using one variable. You can do insolation, you can do south, you can do north, you can do east, and you can do time of day. So this one reported back to us the top 3, which appears to be the one for north, the one for insolation, and the one for time of day, which I was kind of shocked that this one made the top 3. It is what it is. Anyway, considering it's the first one we removed. So as you look at this, you're like, oh, okay, so these are the ones using one variable that are the best. And then there's 2, 3, 4, and then you only have one number 5 because there's 5 variables. It's using all of them. Cool. So what you will have to do with this is look through and try to pick out which of these does the best job. So there's a couple things you should look at. I want a large R squared adjusted, which that's not too hard to do. The only ones that really have bad squared R squared adjusteds are the ones at the beginning. And then this one's the only one that's a little low, so maybe don't use the last number too. Then the rest of these are pretty much all the same. They're off by each other at max like 3%. That's not a huge difference as far as I'm concerned. The next thing you should look at is the S value, just like we do. So I'm hoping you notice that the S values for the first number 2 and then pretty much everybody below the first number 3 are all at about 8. So that's what I'm looking for. I'm probably going to have an S of around 8. So again, they kind of all look the same. Let's look at the Mallows. So 5 is a good one. For the first number 4 is a good one, and none of the number 3s have a good Mallows cup, because with 3 variables we should something around 4. And none of the 2s. So that helps us eliminate. So probably not 2, probably not 3, but 4 and 5 are looking like our ranges. So what I would do looking at these is I would actually pick the first number 4, which might shock you because previously we were saying just use 2. I would actually pick this one because its R squared is relatively high compared to the rest of them. It is one of the highest without using everyone. It keeps its S fairly small. Notice it is one of the smaller S values compared to the rest, and its Mallows cup is right where it should be. So according to what I picked, I would actually use insulation north, south, and east, even though not all of them are significant predictors. So one way you can approach this is you can say, yes, I would choose this model because although insulation is an insignificant predictor in the model, it might be necessary to know how much insulation you're using in the glass to prevent yourself from having too much heat flux. Anyway, and if you remember, this one was 6.7% as its insignificance level. That's not that much bigger than 5%. If it's a judgment call that you're trying to make, it looks like you should include it. And hopefully the best subsets method helped you see that. All right, that's all I got. Go do some math. Where's my pause? There's the button.